All right, we're talking about light. Light's also known as electromagnetic radiation. It's not capital. It's all one word, electromagnetic. Well, electro, what does that refer to? Electro refers to electric fields. What is an electric field? What is an electric field? Well, if you have some physics, you'll know lots about electric fields. But if you haven't, electric field is very simple. Electric field is you have positive charge buildup in one region and negative charge buildup in another region. And so you have this separation of charge, which creates an electric field. And so one part is positive, one part's negative, and then we have an electric field between. A magnetic field is the same thing. You bring a magnet, you're going to have a north pole and a south pole. And so you'll have two regions, a north pole region and a south pole region. Now, electromagnetic fields, is whenever we have a moving electric field, we're going to generate a magnetic field. And so what we see is this. An electric field with light is like this, where we have plus, minus, plus, minus. And light is moving. And so what would you experience if you were hit by light? What you'd experience is, in one instant, you have a negative charge. In the next instance, you have a positive charge. Okay, so this light hits you, and so it's moving. Do you know how fast it's moving? It's moving at the speed of light. Does anybody know how fast the speed of light is? Yeah, we'll probably go with 4 sig figs, 2.998 times 10 to the 8 meters per second. And so it's moving very fast. 10 to the 8 meters per second is extremely fast. And in that instant, or this instant, the light's hitting you, you feel this oscillating field. Now, what things interact with electric fields? Well, charged particles will interact with electric fields because, in one instant it's negative. Let's say you're a positively charged particle. So negative comes by, you're going to be repelled by it. Positive, you're going to be attracted. And so if you're a charged particle, if the electric field's coming like this, you're going to start what we call oscillating with the field, charged particle. Okay, if we have an electric field, then perpendicular to this, we're going to have a magnetic field. But the magnetic field, we're not really going to deal with. So this is not the greatest drawing, but this would be the magnetic field. Magnetic fields are very important. As well. And so you just have north-south, north-south. So if you're a little magnet, what would you do? You'd be flipping, right? Or oscillating with the magnetic field. If you're a charged particle, you'd be oscillating with the electric field. And so this is like a boat, A boat is going to oscillate with the waves. If the waves are moving slowly, the boat's going to be oscillating slowly. If the waves are moving fast, frequently, the boat is going to be oscillating fast, right? Because the boat is at the mercy of the waves. Basically, it's just going to follow the motion of the waves. Well, if you're a tiny charged particle, right? If you're a tiny charged particle, you're at the mercy of the waves here. You're going to be doing the exact same thing the boat's going to be doing. You're going to be oscillating with the field. And so what types of tiny charged particles do you think are, you want to be light, because if you're too heavy, are you going to really be oscillating much with the waves? Let's say you're a freighter, a little wave comes by. Is that going to perturb you at all? Is the freighter going to start rocking with the wave? No. You know, a light particle is going to oscillate. There's a lot less inertia, right? And so, what types of charged particles have you dealt with? Well, you've dealt with electrons, you know, protons, and neutrons. And out of those, are the neutrons going to be oscillating with the? No, not at all. The protons, yeah, sure, the protons are, but the protons are kind of massive. Right? It would be more like anchored in there. But the electrons are light, and so when you think about, you know, this light is going to be interacting with electrons primarily. If you think about matter, matter is made up of protons, neutrons, and electrons. So the electrons would be the ones that would probably oscillate the most with these waves, correct? Because electrons are a lot less massive than the protons and the neutrons. In fact, you know, when you look at what was that gold foil experiment? Who did that one? Rutherford gold foil experiments. When the alpha particles hit the nucleus, did it really ricochet the nuclei out of there like a, you know, like a pool ball hitting another pool ball? You know, no. The alpha particle pretty much just bounced off the nucleus, you know, due to the repulsions. But anyway, going back to this. Okay, so we're looking at this light moving here. And I'm not actually going to go on the order of the book. We're just going to kind of speed things up because I need to do a little bit of catch up. But let's talk about some of the things that we should know about waves like this. One of the things is the wavelength, you know, which we call lambda. The wavelength is the peak-to-peak distance, or the valley-to-valley distance is the same. You know, the valley-to-valley or the peak-to-peak, lambda. Now, these are moving at the speed of light. The speed of light is constant in a vacuum. And so the wave is moving very fast. And so we have this relationship between wavelength and something called frequency. The frequency is how many peak-to-peak cycles or valley-to-valley cycles hit in 1 second. And so if we go from a peak down to a valley back to a peak in 1 second, that would be 1 cycle per second. 1 cycle per second is called a hertz. A hertz. And so we have something called frequency. And the units of frequency are the hertz, and the hertz is a cycle per second. A lot of people leave off cycle and just call it seconds to the -1. The wavelength typically is in meters. And the speed of light is in meters per second. And so we can come up with a relationship. You know, if we take meters and divide it by seconds, in other words, we take meters times the frequency, we should get meters per second, or c. And so the relationship is that c, the speed of light, is equal to lambda, which is meters, times mu, which is the frequency. This is lambda, or wavelength, and this is mu. Is that mu? Yeah. Which is the frequency. So c equals lambda nu. And dimensionally that works out. And so the longer the wavelength, the shorter the frequency, because c is a constant. And so the longer the wavelength, the shorter the frequency, or the lower the frequency. And so long wavelength, lower frequency. Short wavelength, higher frequency. Okay, here's where I'm going to jump ahead. When you think about the strength of waves, right? you know, the energy contained in a wave, you think in terms of amplitude. You know, how big is that wave? A 30-foot wave, you know, versus a 3-foot wave. A 30-foot wave is going to have a lot more energy, right? But when we think about energy and light, we have to think about two things. We think about the amplitude, but we don't actually, you know, calculate the amplitude. Okay, and then we think in terms of frequency. And so I'm going to introduce, this is much earlier than in the book, but the energy of the light is going to equal h nu. H is Planck's constant. And so the energy is directly proportional to the frequency. And so the higher the frequency, the higher the energy. But we know that nu is equal to c over lambda. And so this comes out as hc over lambda. And so the longer the wavelength, the lower the energy. And so what we see here is high energy light. We'll just say high energy light is typically high frequency, short lambda. Whereas low energy light is going to be lower frequency, longer wavelength light. Then this is the way we think about energy. Call it 1. The second way we think about energy is the amplitude. So you might have a certain wavelength or a certain frequency of light, but is it dim or bright? The brighter that is, the more energy you have of a given wavelength or a given frequency. And so when we're thinking about in terms of amplitude, amplitude is related to intensity, the intensity of the light. And this is the second way we think about energy of light. And so whenever we're thinking about, you know, how much energy there is in light, we got to think in terms of two things. We think in terms of the wavelength or the frequency, and we think in terms of the amplitude or the intensity. And people just don't say amplitude, they just say intensity of the light. That is, you know, you might have a certain frequency, right? But that frequency might be 3-foot waves. So every, you know, couple of seconds a 3-foot wave comes by. Or it might be a 10-foot wave. Every 3 seconds, the exact same frequency, every 3 seconds, a 10-foot wave comes by. Well, the 10-foot wave is going to have a lot more energy, right, than a 3-foot wave. And so when we think about light, we think in terms of the exact same thing. You know, a tidal wave packs a huge punch, but, you know, that's based on the amplitude, not on frequency, because the tidal wave's not coming one after the other, right? And so light, we think in the same way. But sometimes we'll just focus on one aspect of the light. And so let's look at one aspect of the light and see what that does. In terms of light, there are many types of light, but they're all the same in terms of electromagnetic radiation. The only difference is their wavelength or their frequency. And so when we look at light, we can go, let's start off with the highest energy, or let's start off with the lowest energy. Let's start off with low energy. Low energy. Now, you know, low energy, you know, we aren't talking about the amplitude because the total energy can be quite high. And so let's get rid of the intensity because we can change the intensity. We'll just keep the intensity the same for all these and then just look at it in terms of energy. Lowest energy light would be the longest wavelength, lowest frequency. And so what are some of the longest wavelength, lowest frequency forms of electromagnetic radiation or light that you know? What's the lowest one that you memorized in Chem 4? What is the longest wavelength, lowest frequency light you memorized? Radio waves. Okay, we'll go with radio waves. Radio waves, do you usually memorize the wavelength or do you usually memorize the frequency of radio waves? Usually frequency. For example, AM radio, I don't know if anybody uses AM radio anymore, but AM radio has a frequency of what? Yeah, like kilohertz, right? And so radio waves, we're looking at kilohertz. Kilohertz, 1,000 hertz or so. 1,000 hertz means, what's the wavelength of that? And so let's try to figure out. 1,000 hertz is equivalent to 1,000 cycles per second. And so in 1 second, 1,000 waves, peak to peaks, come by you. That's moving very fast, isn't it? Well, it is. It's moving at the speed of light, and so that's a lot of waves. What is wavelength? And so normally, I don't know what the wavelength is, so let's go ahead and calculate the wavelength. Lambda is equal to c over nu. C is 2.998 times 10 to the 8 meters per second. Nu is going to be 1,000 per second, or seconds to the minus 1. And so the seconds cancel, leaving us with meters. And so this is going to be, well, 10 to the third, 10 to the 8th. This is going to be 10 to the 5th. And so it's going to be 2.998 times 10 to the 5th meters per second. Well, 10 to the 5th is, well, that's a kilometer is 10 to the third. And so this would be 299.8 kilometers, or about 300 kilometers. Is that right? And so think about the wavelength, the peak-to-peak distance is that right? Could that be right? A peak-to-peak distance of 300 kilometers? Does that sound right? And so the peak of one wave, top here, then the next one would be 300 kilometers away? That doesn't seem right. It's a huge distance. In other words, the wavelength, you wouldn't even be able to see the other peak if it was fixed in space. Would you be able to see the other peak at 300 kilometers away? No, it just doesn't seem right, but did I make a mistake? No, I guess that's right. According to my calculation, this is right. And so, but you know, the speed of light is incredibly fast because even though a peak to peak is 300 kilometers in distance, 1,000 of those pass by in a second.
Shouldn't the values be meters per second squared? Since it cycles over second, the second doesn't cancel out with the top, does it?
Cycles are just, you know.
Or the second, or so it cycles over second. So the second would just sorry.
Okay, no, because the cycle, I should say cycle per second, maybe. How about that? It was just plural, cycles. The S is not related to cycles per second. Amen. And so, anyway, if you're, let's say you're an electron, right? And it's oscillating like this. You know, you're going to be oscillating pretty fast, 1,000 if you're an electron, right? And you get caught in this wave. If you're an electron caught in this wave, you're going to be oscillating at 1,000 cycles per second. Well, what do radio waves do? Well, they excite electrons. What's a good radio wave antenna? You know, if you want to make a good radio antenna, what would you make it out of? Let's say. Would you make it out of wood? You think well, the electrons in wood, let's excite the electrons in wood. Well, the problem with exciting electrons in wood is they're all caught up in the bonds, you know? They're kind of stuck. And so these electrons are more anchored. You want loose, you know, free-moving electrons, not something that's anchored. So where do you see loose, free-moving electrons? Let's say your antenna broke on, if you have an old car, your antenna broke on the car. A lot of people, you don't see this as much anymore, but a lot of people used to put coat hangers in place of their antenna after they break. Well, why didn't they use a piece of plastic or something like that? Yeah, well, you know, coat hangers do conduct electricity. That means that the electrons are easily excited in metals, and so they excite electrons in metals. Radio waves. Okay, after radio waves, what do we have? Microwaves. Microwaves, you know, microwaves have, what are they, millimeter wavelengths? Is that right?
The AM radio has like 1,000 kilohertz. It's like 10 to the 6.
1,000 kilohertz. Ooh, that's right, kilohertz. Yeah, I'm just doing 1 kilohertz. So if it's 1,000 kilohertz, then
it's like a 10 to the 6.
Yeah, that'd be 10 to the 6. And so if you're tuning in, you're right, AM 1040 or something like that, huh? 1040. And so 1,000 kilohertz. 1,000 kilohertz means the wavelength is going to be
10 to the 6.
10 to the 6. So that would be
Still pretty big.
10 squared, so that would be still pretty big, yeah. And so it would be 0.2 kilometers, or 299 meters. Okay. 1,000 kilohertz would be about 299 meters. Yeah. Lambda. So 300 meters is a pretty long distance between peak to peak. What about microwaves? What are microwaves at? Well, 1,000 kilohertz is also known as a megahertz. And so I was going to use megahertz for, not megahertz. Actually, radio waves, AM is kilohertz, FM is megahertz. And so FM would be 100, let's say, megahertz. 100 megahertz would be equal to 1 times 10 to the 6, 7, 8 times 10 to the 8 seconds to the minus 1. And so FM radio would have a wavelength, well, 10 to the 8 divided by 10 to the 8, it's going to have a wavelength of about 3 meters. And so FM radio is about 3 meters if it's at 100 megahertz. Microwaves are at gigahertz. Like a microwave oven, I think, is 4.5 gigahertz. .5 gigahertz, what's the wavelength of that? Well, giga, what is a giga again? So gigahertz would be 4.5 times 10. So we go from kilo to mega to, okay. Times 10 to the 9th. Is giga 10 to the 9th? Let's say you have a terabyte is what? A gigabyte is what? A megabyte. So it goes mega, giga, tera. Right, for your hard drives? Is that right? And so this would be 10 to the 9th. Right. 10 to the 9th seconds to the minus 1. if it's 10 to the 9th, well, we're going to get 10 to the 8th, 10 to the 9th. That means the wavelengths are on the order of centimeters. Centimeter wavelengths. Like 8, 10 centimeters. I think your microwave has like an 8 centimeter. And your microwaves are like standing waves, you know? And you can generate standing waves. And so, you know, there could be hot spots and cold spots maybe in your microwave, right? And so probably the best thing to do is either rotate the food or move it, you know? So if you have a wavelength of like this, you might be in a 0 amplitude region. But what do microwaves do? Well, would you put a metal inside a microwave? Why not? Have you ever done that? Have you ever put metal in a microwave? What happens? It sparks. You know what? If it sparks, the electrons are getting what? A little bit too excited? Yeah, you don't want that to happen. But microwaves do other things too. And so it's not just electrons that have a charge, but molecules also have a charge, polar molecules. One polar molecule in particular, water, has a positive region, which is called delta plus, and a negative region, which is delta minus. And it turns out that this frequency, you know, is enough to rotate water molecules. And so microwaves can rotate small molecules. They have to be polar, of course. Because if they're non-polar, they aren't going to interact with oscillating electric fields. Right? And so they rotate small polar molecules. You know, but let's say you have a this happens to me quite a lot, is because I have some ceramic ware, and in the glaze of that, you know, sometimes there's like metal ions like cobalt. You know, cobalt gets extremely hot in microwaves. So if you have a glaze with cobalt in there, you know, why does cobalt get so hot? Well, cobalt has a lot of electrons, and those electrons can get excited, generate a lot of heat. And so if you have things with a lot of electrons, like metal ions in your glaze, those are going to get quite hot as they interact with the microwaves. The electrons interact. But primarily, we'd just say rotate small molecules, excite electrons in certain species. It's microwaves. After microwaves comes what? Infrared. Infrared, actually, this has, now we're starting to get more in terms of wavelength, millimeter wavelengths, you know, or micrometer wavelengths. Millimeter is probably more towards the microwaves. Actually, no, millimeter should be towards microwaves. Micrometer is more towards infrared. And so, you know, the wavelengths are getting a lot shorter. With infrared, well, what are the frequencies? People don't usually think about the frequencies, more towards the wavelength. What are the, what does an infrared lamp do? Well, usually infrared lamps keep food warm. And how do they keep things warm? Well, it turns out what the infrared can do is infrared causes vibrations of bonds, of polar bonds. In a polar bond, what we have is, let's say we have a carbon atom here bonded to an oxygen atom here. The carbon might be bonded to other stuff. We have a polar bond here because the oxygen end is delta minus, the carbon end is delta plus. And so if we have an oscillating field here, you know, plus, minus, and this hits this, then it's going to cause this to oscillate, the bond to oscillate. As the bond oscillates, because the atoms are charged here, then that's going to cause it to heat up. And so infrared causes vibrations. of bonds to occur. Okay, after infrared comes visible. And so here we start thinking in terms of wavelength for sure. Now visible has a distinct range of wavelengths. Do you know the range of wavelengths that we have for visible?
4 to 600.
Yeah. And so we're going from lower energy to higher energy right now. So low energy visible has longer wavelengths. So we say 760 nanometers. And at the highest energy we have 390 nanometers. Now the thing with infrared is you can't see it. Microwaves you can't see, radio waves you can't see, but visible light we can see. You know, see that as white light or whatever, colors, etc. Do you know what color 760 nanometers is? Call that red. 390 nanometers we call violet. Do you know the colors of the rainbow? If you haven't memorized it, the easy way to memorize is Roy G. Biv, where it goes red, orange, yellow, green, blue, indigo, violet. And the range here is 760 to 390. 760 to 390 is important, so you should memorize that. It's the range of visible. That way you can guesstimate. You know, for example, where's green, roughly? Green is kind of halfway between, so green would be, well, this is 800, that's 400, so halfway is going to be around 600 nanometers should be green, right? This is just a guesstimate. But it's better to know that than to not know anything. Well, you know, what are the frequencies of this? Normally we think in terms of wavelength after we transition here, then we think of the light in terms of wavelength. But, you know, also we should know the frequency, although I'm not going to ask you to memorize the frequency. What would the frequency of these lights be? Now, what is a nanometer? So, for example, what is the red light frequency? So if we go 760 nanometers equals what frequency? And so the frequency is equal to C over lambda. And so C is 2.998 times 10 to the 8 meters per second. Lambda is 760. Now what is a nano? 10 to the negative 9. Times 10 to the negative 9 meters. Meters cancels out, and that should give us a frequency. Our frequency is, can somebody calculate this? I don't know. I don't know. I just, you know, and most people just memorize the wavelengths. The two bordering wavelengths, 760, 390.
Is that 10 to the negative 9 from the bottom?
Yeah.
3.94 times 10 to the 14.
Times 10 to the 14 hertz. 10 to the 14 hertz, what is that? Well, oh, what is 10 to the 12? Terahertz, right? 10 to the 12, so this would be 394 terahertz. But whatever. I don't really, you aren't going to do much with the frequency except maybe once in a while calculate it. So we focus on the wavelength. The reason we focus on the wavelength is, let's say there's light. What is this? Is this mine? Let's say there's light of wavelength 1,000 nanometers. Where's that? 1,000 nanometers. Is that in the visible? No, it's in the visible range. 1,000 nanometers should be infrared. Infrared. And so by knowing 760, well, we know 1,000 nanometers is going to be infrared, or somewhere, maybe 1,500 nanometers. Where would you guess that is? 1,500 nanometers. Infrared. 2,000 nanometers? Infrared. It's not until you get to centimeter that we get into microwaves. And so there's going to be a huge span of wavelengths for infrared. And so we can kind of get an idea. Now, if I said, well, 1 billion nanometers, then that would be tricky because, where is that? 1 billion nanometers. Then you'd think, is that centimeters, millimeters? What is that? Meters? Likewise, if we have light at 150 nanometers, what is that? Well, it's beyond violet. And so beyond red we call infrared, beyond violet we call ultraviolet. But I forgot to say something. What does visible light do? Visible light's going to have a certain frequency. 394 terahertz. It's a very fast frequency, isn't it? What can that do? You know what this can do? This can excite electrons in matter, including things like wood, plastics. It excites electrons. And so this excites electrons. In matter. When those electrons get excited, we see colors here. Because, the electrons, depends on where those electrons are located. Some electrons require a little more energy, some require a little less energy to get excited. And as those get excited, let's say some electrons require blue energy to get excited, then we eliminate blue out of the rainbow. And if you eliminate blue out of the rainbow, the color is different. Let's go to ultraviolet. Ultraviolet is going to have lambdas that are going to be shorter, right? And so what should we say the wavelengths of ultraviolet are? Less than 390 nanometers on down. Usually over a couple of orders of magnitude. And so we go ultraviolet. Ultraviolet is going to be much higher frequency. And ultraviolet, what it can do is it can break bonds. Here, when we excite the electrons, we don't necessarily break the bonds. Here, with ultraviolet, we break bonds. And then we get to, this breaks bonds in matter. Then we get to X-ray and gamma ray. Both of these are called ionizing radiation. Ionizing radiation excites electrons so much that the electrons break off from matter, and we ionize it. And so these are going to be very short wavelengths. Extremely short lambdas. And so how short? Well, X-rays have wavelengths around an angstrom. You know what an angstrom is? Have you heard the term angstrom? An angstrom is 10 to the minus 10 meters. Why is that important? You should know what an angstrom is because you know about how big are atoms. About how big are atoms? Atoms are on the size order of 1 to 6 angstroms in diameter, right? 1 to 6, 7 angstroms. And so angstrom is about the size of an atom. Well, X-rays have about the same wavelength. Gamma rays are much more shorter than angstroms. And so gamma rays have wavelengths much smaller than an atom. Well, what do X-rays and gamma rays do? They knock electrons off matter. Knock electrons off matter. These are extremely high frequency. Forms of radiation. All right, so this is the electromagnetic spectrum here. You know, we have cosmic rays as well, which can be very high energy. Well, we'll stop here. Actually, I guess we went more than an hour, huh? Well, let's take a break and then we'll continue.